Assalamualaikum and hi everyone. In this video, we're going to learn about voltage divider bias configuration. But before you proceed with this presentation, I hope you watch my presentation on emitter bias configuration. And also, I hope you have better understanding on Thevenin. Okay, for this configuration, we have two method of analysis, which is exact analysis, and also another one is approximate analysis. In exact analysis, I think we can do the same way with the previous presentation, which is we have to use KVL on BE loop and also KVL on CE loop. But for the approximate analysis, we have to check the condition first, which is beta RE should be bigger than 10 R2. Otherwise, we cannot use the approximate analysis. We have to use the exact analysis. And if this condition is met, so we assume that VB equal to E Thevenin. I will explain later in this video. Okay, for the first analysis, which is exact analysis, first we need to know the difference between emitter bias configuration. Okay, for the emitter bias configuration, there is RB here. Okay, we have only one resistor to be the input for the base terminal. But for the divider bias configuration, we have two resistor, and then this one going to be input for the base. For that reason, we have to do some simplification for this input. Okay, what we need to do is we have to rearrange R1, R2, and also VCC. Okay, in my previous video, I explained how to split the VCC here. So I think we need to do the same thing, which is we have the VCC on the left and also on the right. Okay, so we have two VCC. Okay, and then connect to ground. So we just redraw this circuit. We have VCC. Okay, we have VCC, and then from the VCC we connect to R1. Okay, connect to R1 here, and then from this point is here. So this point will divide by 2, which is one connection connect to the base terminal is here, connect to base terminal, and another one is connect to R2 here. Okay, so the equivalent circuit here, the equivalent is here, so it's connect to R2, and then from the R2 connect to the ground here. So this is the ground. Okay, so this is for the BE loop, and then for the CE loop, I think it's same with the emitter bias configuration is here. This is the equivalent circuit. So what we need to do is we have to simplify this part, the input part. So how we going to simplify the circuit? We have to use the Thevenin, okay, Thevenin theorem. In Thevenin, what we need to do is we have to simplify the circuit to be only one resistor and also one power supply. So for the resistor part, what we need to do is we have to short the power supply, which is we have R1 here, and then we have the R2 here, and for the VCC we have to short the VCC, and then from here we have one R1, and this is one we have R2. So meaning that R Thevenin is total impedance looking from here, which means from right to the left. So if you look from right to the left, you get the parallel resistor of R1 and R2. So meaning that your RTH, R Thevenin is equal to R1 parallel with R2. So the calculation is will be R1 times R2 over R1 plus R2. Okay, this is for the R Thevenin. Okay, so the total RTH look from here is R1 times R2 over R1 plus R2. So how about the ETH? Okay, ETH also we can look from here, this point of view. So meaning that this is the ETH. If you look here, actually ETH is equal to VR2. The circuit is will be like this. In to find the ETH, we cannot ignore the VCC. We have to consider the VCC. So this is your ETH. It's here your ETH. So this one plus and minus. If we treat this one, ETH is parallel with R2, VR2. So meaning that ETH equal to VR2, so equal to voltage divider R2 over R1 plus R2 times VCC. So this is the value of RTH and ETH, RTH and ETH. So if we make this simplifications, so on your BE loop is going to be easy. Let's compare with the emitter bias. Okay, emitter bias configurations. Your power supply is VCC. Okay, and also your input resistor to base is RB. But in this case, your input resistor is RTH and also your power supply is ETH. So I think we can just change the value. Okay, but never mind, we can just do the KVL. Actually we can do the KVL using clockwise or anti-clockwise. For in this example, I'm going to use clockwise. So start from ETH, the KVL will be minus ETH plus IB RTH. Okay, RTH no RB. And then we have a voltage drop at the transistor. We label as VBE. The value is 0.7. And then just substitute, oh sorry, IE and RE equal to 0. We have to find the value of IB first. So IE we have to substitute with the value of we have to represent in terms of IB. So IE equal to beta plus 1 times IB. So if you substitute the value here, and then you will find the value of IB is equal to ETH, okay, not VCC, minus 0.7 or VBE, minus VBE over, we have the RTH here, plus beta plus 1 times with RE. So this is the value for IB, and then to find the IC, we can just use the equation of IC equal to beta IB. And then for the IE, we can use the equation of IE equal to beta plus 1 times with IB. Okay, this for the BE loop, the analysis for the BE loop. Okay, and then for the CE loop, I can say it's totally same with the emitter bias configurations. So I can just proceed with the KVL here. KVL for the CE loop is, for this one we use the clockwise, so it should be positive VCC and then minus IE RE, and then we have the voltage drop at the transistor, we label as VCE, and then we have voltage drop at the ICRC, okay, equal to 0. Okay, this equation is actually same with this equation. You just rearrange the equation, you can find that this equation is totally same. So usually for the CE loop, we're going to find the value of VCE. So VCE, we will have VCE equal to VCC minus ICRC minus IE RE. Okay, that's all for the CE loop. Okay, and then for the load line analysis, again, I can say this one is totally same with the emitter bias configurations. So uh, just for your reminder, that's to we have 2 points, which is we have to find the IC saturations, and also we have to find the VCE during IC equal to 0. So to find this first point, what we need to do is we have to substitute the value of VCE equal to 0 volt, okay, into the KVL equation. So let me write down here VCC plus IC is right now is going to be IC saturations, and times with RC plus VCE equal to 0, and then IE right now is going to be IC saturations. Okay, why? You have to find out in my previous presentation, and then is this one equal to 0. Rearrange this equation, you will find out that IC saturation is equal to VCC over RC plus RE. It's totally same with the emitter bias configuration. So, and then for the second point, what you need to do is you have to substitute the value of IC equal to 0. Okay, substitute into the KVL equations. So you find out that the value of VCC plus, okay, IC is 0, so this one will be 0, and then plus VCE, since this one IC is 0, there is no input, so there is no output, so IE also equal to 0, so you will have 0 here equal to 0, and then you will find that the value of VCE is equal to VCC.